Hello everyone, we are here in our one-dimensional kinematics notes, and this specific one is example number 3 in the vertical section of the notes. So we have a person throwing a ball, has a velocity of 15 meters per second upwards. The ball leaves the person's hand 1 meter above the ground. We want to find the time the ball will take to get to the top, the time the ball will take to get back down to the same position from which it started, the time for the ball to reach the ground, the maximum height of the ball from the level from which it was thrown, and its velocity when it strikes the ground. So what I'd like you to do here is stop and think about this, draw your picture for how to represent this, and then when you think you have a picture, go ahead and pick up where you left off, and we'll see where to go from here. Alright, so here we are back with our picture. Now you'll notice this looks a little confusing to begin with, but I'd like to take a little time to explain what I have here. Of course, the first place that we're dealing with here is where the ball starts. Okay, and this ball is thrown with some initial velocity of 15 meters per second, and again, it's in an upwards direction. It reaches some highest height, and of course, we always know that the ball has a velocity of 0 meters per second at the highest height. We know that the acceleration, of course, during this entire time interval is always due to gravity. We're ignoring air resistance. So it's always going to be the 9.8 meters per second squared in a downwards direction. When it gets back to the same level, I call this snapshot C. And when it gets here, it has an equal magnitude of velocity. In other words, the speed is the same. So 15 meters per second, 15 meters per second. But again, note that the velocity is in the opposite direction because it's now headed in a downwards direction. And lastly, we're asking about this ball when it is striking the ground. Now, something to keep in mind here, this is a common misconception, is that when it asks these questions about the ball striking the ground, it's not after it's come to rest on the ground. Okay, it's that instant as it's just getting to the ground level. The ground has not quite acted on the ball yet, so there's no force on the ball because of the ground. It's that instantaneous velocity as it hits the ground. So again, it's like we're taking that snapshot. It's a picture of the ball at that instant it strikes the ground. So it hasn't come to rest yet. So that is why you'll notice here that I do have a velocity that is a non-zero. This is some velocity for this ball. All right, so again, this is maybe a lot of things happening here. You could certainly draw multiple pictures, but what's going to be important here is that when we take a look at this problem, we know between what two snapshots are we looking when we solve our problem. So if we go over our knowns, of course the entire time interval here, we have an acceleration, a positive direction. Again, it's down, and my acceleration is down. So it's always the 9.8 meters per second squared. We have a velocity at point A, it's in the negative direction, here it is there, and it's 15 meters per second. We know at the top, again, the velocity is 0. So we know that. The velocity at this point is 15 meters per second as well. And we know that the displacement looks like from C to D, that's from this point to this point, is 1 meter. I don't have it labeled here, but that's with the value at least. But that's what that would be. And again, this would be the same displacement from A to D as well. So ultimately, whether we go from A to D here or C to D, it really is not important. So let's look at how I went about this. Part A asks us to find the time from, and if maybe I should pull back up what we were looking at here. Part A says the time for the ball to get to the top. So you'll notice here that in my problem, this is from snapshot A to snapshot B. In the next one, says the time for the ball will get back to the same position from where it started. So if I go back here to my picture, that would be from time A to C is what we're looking for here. And I think this third part here asks us the time for the ball to reach the ground. So notice here, we're dealing with the entire distance from A the whole way to D. Part D, let's go back and see how it was worded. Part D says the maximum height from the level from which it was thrown. So if we go back here, that looks like it's from A to B. So in other words, this is where it started, and that's where it's going. So we're looking for this delta y in here. And we are also looking for the velocity at point D. And again, I have this little vector symbol over it just to remind us that, hey, this is a vector, so we need to worry about both the magnitude and the direction. So at this point, we've got a lot to think about here. I'd like you to stop and think and figure out which equation or equations you might need to use to solve this. All right, so here we are with part A. And in part A, we know that, again, we're going from snapshot A to snapshot B. That was the kind of the level at which it was thrown from, going to the very top. Again, since we know that in this case, our final velocity is the point at which we picked to be the end point for this part of the problem, we know that it stops at the very top of its path. So that's why our final velocity is 0. Again, down was positive, so my initial velocity is actually a negative value. And we have our AT here as well. So solving for t, we get the v sub o over a, and we know the v, and again this would be the velocity at point A, and of course we know the acceleration. So that shouldn't be too bad to figure out. Moving on to part B, I can use the same thing here, and again make note that in this particular part of the problem, I'm going from snapshot A to snapshot C, and because we wanted to know how long would it take until it got back to the same position. Now, keeping in mind from a previous problem, honestly, we could have just taken the value we get here and multiplied it by 2. But I chose to show you a little different way to do this. Again, taking advantage of the symmetry involved, the fact that it's the 15 meters per second. In fact, let me just go back to it here. Right here we go. Due to the fact that it's very symmetrical in nature, the fact that it leaves with 15 meters per second going upwards and it comes back with 15 meters per second downwards, we can kind of take advantage of that and plug those values in here. So again, to get that time, we would end up with actually twice the time of here. Moving on to part C. Part C, I actually make a little note here, is I'm going to use the same equation. But the problem is we don't know the final velocity yet. We don't know the velocity at point D. So we are actually going to find that in part E. So I said, hey, why don't we actually do that part first, come back, throw this number in here, and we will end up with a time, or the total time here. So we're gonna kind of hold off on those numbers, and we'll come back to that. Now there is another way to do this, and I will talk about that a little bit at the end. But this is just one way. Remember, there's always more than one way to solve these things. Let's move on to part D. Part D asks us to looks like find how high does this ball go. So again, in our picture, let me go back to our picture. Right here we go. That's our delta y, how high from this location. And again, since the delta y is in the upwards direction here, and our positive direction is down, that is why you will see here the negative on the delta y. We also know that the final velocity at the top, that's point D or snapshot D, whatever you want to call it, that is 0. And so therefore this cancels out, and we end up algebraically looks like we get the delta y equals 1/2 times v sub o times t. And again, now this is going to be really important here, is you got to remember which t to put in. We've just solved for 3 different t's in this particular problem. So you got to keep in mind that the t you're talking about here is the time from A to B. So you got to be kind of careful here when you're making your substitutions, that you know what you're substituting in, and you don't just blindly put in any old t, because it has to be very specific. It has to be the time from A to B. All right, part E. Again, we were going to use this value here to actually find the time in part C. So effectively, when I do the calculations in the solution section, you'll actually see me take the number here first and then put it over here. Again, keep in mind there is another way to go about it, and I'll kind of show you that later. But at any rate, since we didn't know time for this part, I said, hey, why don't we try the time-independent equation? And again, keeping track of all my positives. And again, from this one, I went from C to D, and it looks like I'm trying to find the final velocity here. Again, you could certainly go from A to D as well. Notice your initial velocity in this case would be negative, but mathematically speaking, I'd ask the question, does this really make a difference? In other words, going here back to our original picture, if I put this picture, this snapshot in, it would be a negative value for the 15. Over here, it's a positive value for the 15. So originally, going from here to here, it's a 1 meter positive displacement. From here to here, it's a 1 meter positive displacement. So my question is, would it really matter? Going back to our equation here, think about what that means in here. That means we're either putting a positive in here or putting a negative in here. But look at what the equation tells us to do. It tells us to square this. And since this is being squared, a positive or negative here makes absolutely no difference whatsoever. So just keep in mind that I chose from C to D, but there's no reason I had to do this. This is just what I chose to do. I didn't just, a choice that I made. So again, solving everything out here, looks like I'm going to end up with this here. So let's look at putting the numbers in and check out how that's done. All right, so we're back. We're ready to put the numbers in. Part A asked us to find the time it took to get to the very top. Again, we already solved for the equation earlier, so basically now it's just a matter of putting numbers in. 15 meters per second was the original velocity at point A, and we have an acceleration of 9.8 meters per second, and that's in a downwards direction. When we do the algebra, I'm showing my units here. I've done my unit analysis over here, just within the problem itself. Always multiply by the reciprocal here. That's why it reciprocates over here. One S cancels out one of these S's. The meters cancel out, and we're left with seconds. That's a good thing. We want seconds as an answer. Likewise, part B, you'll notice here, we have a 15 meter per second velocity at the beginning and a 15 meter per second velocity at the end. And again, this is because that symmetrical thing, one is up, one's down. We've already taken care of the directions back in the equation, so that's why you don't see the positive or negative here. But notice again this time, it's twice the time that it takes. So again, we could have just found this value and just multiplied it by 2, but ultimately this is how I chose to do it. Now going back to part C, remember I said we'll actually find the value of the final velocity, and we'll actually use that down in here, and you can see that I've done that. But again, I'm solving here using the equation that I came up with, and I end up with 15.64 meters per second. And remember, when you take a square root, it's always positive or minus, and again, this would indicate to us that one of these solutions is irrelevant to our problem. Solving for our delta y is 11.5 meters. And our last one here is solving for the total time. And again, something to keep in mind here is that you need to make sure you put the right values in here. We're dealing with the velocity or the speed at the very bottom, and in this case this was the velocity at point C. So I'm using these values again, putting them in, and I end up with 3.13 seconds. And so in the very end, this is what I get for my responses.